get into some preliminary material today, and then if we have some time, so we'll talk a little about the introduction to electricity and magnetism. Then we'll talk a little about the electromagnetic spectrum, and then if we have whatever time is left, we'll get into Chapter 2, Material and Electric Charge Line. So again, just reminders, reading quiz due on Wednesday, and you can get that one through Blackboard, the quizzes folder, your general resources, again, the homework, first couple homework assignments there, learning expert TA and the math review, that's also in there. Math review is stuff like making sure you can remember how to do algebra, basic trigonometry, vector calculations, things like addition, subtraction, dot products, cross products, things like that. Okay, so it should not be too long, hopefully. All right. Next up, I wanted to make sure that I have passed something else to you. So, as I mentioned, we will be doing some in-class activities, and one way that I like to do these is get some feedback from you by using these response cards. I'm going to pass these out to you. And these. There we go. Okay, so oftentimes some of these in-class activities will involve sort of multiple choice questions, in which case then you can use this little response card. You can fold it up. For example, if you want to vote for B, you fold it in half, fold it in half again, fold it for B, vote for A, whatever I can see. Okay, whatever you think the answer. Okay. All right, so the way this is going to work, there's only one rule, and that is you always have to vote. Okay, so even if it's just a guess, you always have to vote. Education research has shown that students who attempt problems, even if they're not exactly sure of the answer, learn more than those who don't attempt at all. Okay, so even just by trying, you tend to learn stuff. I do like to have students a chance to actually think about things, though, beforehand. So I will usually give you some sort of prompt. I'll say something like, please vote now. In which case, that's the point in time you can hold your card. Okay? Oftentimes, then, we'll go through a three-step process. Sometimes we'll go through a three-step process. We'll give you the question. We'll vote. If we don't have a strong consensus, then I may ask for some discussion and with your colleagues. And then after some discussion, then we may vote again and see if there's a good consensus or not. Okay? So let's go ahead and do a practice run with this. Okay? So here's the question. On my direction, answer the following question. What is your favorite activity of the following list? A, reading, B, eating, C, listening to music, D, watching television, or E, studying physics? Should not be voting yet. Should not be voting yet. Cards out here. Please vote now. Take a look here. D's and B's. Mostly D's and B's, a few other answers here and there. So we got eating and watching television. A few E's, that's good. That's good. So hopefully we more E's by the end of the term. All right. I think you get the idea, right? Yes? Any questions here? So that's the good. All right, so let's start off here. I just want to do a little bit of brainstorming. So I'll discuss this, of course, about electricity and magnetism. So I want to know, what do you think of when you think about, let's start off with electricity. Give me some examples of what you think about when you think about electricity. Just raise your hand. What do you got?
Light bulb.
Light bulbs, all right, that's a good one. Light bulb. And electricity run light bulb. What else? Yep.
Wiring cars.
Wiring in cars, okay. Wiring in cars, all right. And wiring in general, I suppose. Okay, what else? Yeah.
Electrons?
Electrons, those are important for electricity, I agree with that. What else? Keep coming up, yep.
Copper wire?
Copper wire, okay. Insofar as it's carrying electrons, I suppose it's, yeah, electricity. Yep.
Current?
Current, okay, yeah, we'll talk about current later in the course, for sure. What else? Yeah.
Ohm's law?
Ohm's law, okay, yep, we'll definitely get to that as well. Ohm's law. Yep.
Voltage?
Voltage, yep. Voltage, definitely get in there as well. What else? Anything else you think about? Anything about electricity? Yep.
Resistance?
Resistance, okay, yep. That's Ohm's law as well. There. And
Amperage?
amperage, okay, yeah, has to do with current. Okay. All right. Anything else comes to mind? Yep, one more.
Benjamin Franklin?
Benjamin Franklin, all right, B. Franklin, all right, here we go. There we go. And I say one more hand over here. No? Okay. All right, good list, yeah, good starting list here. Lots of things that are very common in our everyday life, right, in this room even. So we're getting to most of those things, actually. I'm not sure how much we'll talk about Ben Franklin. Talk a little bit about Ben Franklin. All right, let's move on. Magnetism. What do you think about when you think about magnetism? Give me some things.
Motors?
What is it?
Motors?
Well, motors, yeah, great. Example, yeah. Motors definitely usually involve magnets of some sort. Yeah.
Isn't a watch have magnetism in it?
Maybe. I'm not sure. Depends on what kind of watch. We'll put it down. And if it does have a little electric motor, it might. Yeah. What else?
A compass?
Compass, yeah, nice example. Want to see where the direction of the magnetic field is of the Earth? Need compass. What else? Yeah.
Fridges? Fridge magnets?
Fridge magnets. Fridge magnets. Yeah, okay. Yeah, fridge magnets. I've got a good example. Fridge magnets, absolutely. Fridge magnets are quite interesting, actually. What else? See, fridge magnets. Yeah.
Poles?
Poles. Yeah, magnets have poles. So we'll talk about magnetic poles. Okay. Anything else here about magnets, magnetism? Yeah.
Generators?
Generators, okay, yeah, generators. It's kind of the opposite of a motor in some sense. Often do involve magnets. Yeah.
Fields?
Fields, okay, the magnetic fields in particular, yep. We'll put that down. Maybe one more. So lots of great examples here. I think it's a really nice list, what we've got. And so really our goal then, take a look at this list, there's lots of things that involve electricity and magnetism, or sometimes both in our everyday lives. Our goal here is to really understand the basic physical principles that underlie those devices or applications and see if we can explain them using physics. That's our goal. So we'll see how much we can get to during the term. All right. In particular, another thing I want to talk about in this class, we'll get to sort of periodically, is wireless technology. So most wireless technology involves electromagnetism. So can you give me some examples of what you think about when I say the word phrase wireless technology? Yeah.
Bluetooth?
Bluetooth, yeah, nice example there. Very common nowadays. Lots of devices, Bluetooth, what else?
Wi-Fi?
What is it?
Wi-Fi?
Wi-Fi, of course, yeah, Wi-Fi. Great. What else? Yeah, I'm back.
GPS?
GPS, nice example. Yeah, GPS is definitely wireless. Something over here.
Wireless charging?
Wireless charging, yes, indeed. Okay, wireless charging. Nice example. Anything else? Yeah.
Satellite data?
Satellites, okay, yeah, satellite communication, I guess we'll call it that. Communication, okay. Let's see, what else? Yeah.
Radios?
Radios, yeah, nice example. Okay, anything else you think about? Anything else? One more maybe? Okay, pretty good list, pretty good list. Here's a list I came up with, and let's see how many we got in this list. So we got radio, television. You can still get over there television. Not many people do it, most people get cable, but you can still. Remote control, that's one we didn't mention. But oftentimes remote controls are wireless, of course. Cell phones, that was a big one, we didn't get that one. But that's obviously a big example. Wi-Fi we got, Bluetooth we got, GPS we got, inductive charging, wireless charging. Another one which is coming up, it's probably not really available yet in most cases, but vehicle-to-vehicle communication. That'll be something that will be emerging in the future. and just something simple like a personal radio transceiver or a walkie-talkie if you like. Okay, those are all examples of wireless technology. I'm sure you can come up with others as well. Okay, so in particular, I'm going to talk a little bit more about some applications here. So, you know, let's take, for example, cell phones, right? Cell phone in the pocket. These are great until they don't work anymore, right? So let me give you an example. So, anybody heard of Hurricane Helene back in 2024? A few people? Let me raise your hand. Okay. A few people. Okay. So this was a hurricane. It's Category 4, 140-mile-an-hour hurricane that made landfall in Florida. Went up the East Coast. Okay. Once it got up into Northern Carolina, especially up in the mountains areas, this is what happened. Right. Huge amount of rain came down, massive flooding, power, water, and cell service were all knocked out. Right. Nothing left. And so the question is, what do you do under these circumstances, right? Well, one thing you can do is you can use vector radios. So this is an example of a map of what is called WinLink traffic. So WinLink is a specific protocol. Essentially allows you to send the equivalent of email, but over the radio. So you can send it from radio to radio. You don't need the internet to do this, okay? And so you can see during this time, a few days when the hurricane made landfall, there was a lot of communication going on, right? People had to get supplies, they had to get first aid, they had to get lots of things during this period. Okay, so this is an example of how wireless technology can be, life-saving in some cases. Now, there's a whole bunch of different what are called personal radio services, and I'm just going to hit a few highlights here just to give you some sense of this. So the most common one is called the family radio service. Anybody hear of family radio service? Okay. If you've ever used a walkie-talkie, maybe people use walkie-talkie. Okay. If you've used, lots of people. Okay. If you've used walkie-talkie, you've used family radio service. Almost all the ones you buy in the store are that. There's a kind of a one that's oftentimes used more for business called the general mobile radio service, but shares the same sort of frequencies. Short range, low power, does the job though if that's what you need to do. There's a few other ones, multi-use radio service, a little bit wider, longer range, fewer channels. Citizen band, anybody hear Citizen band radio, CB radio? Okay, not as popular as it used to be, a few people. Okay, great. Yeah, a little bit larger range, about 40 channels. Anybody boaters out there? Marine VHF, use your boat radio, okay, use radio on a boat. Yeah, oftentimes you'll be in that Marine VHF band. That has an even larger range, oftentimes, partly because you're over the water, partly because of the way it's set up. But then the last one is amateur radio, which is what I'm going to talk about a little bit more. And the reason I'm going to talk about that a little bit more is because, first of all, there's essentially almost an infinite number of channels available. Has many different kinds of uses, and in fact, you can communicate with people all over the world under proper setup. So in particular, amateur radio is a personal radio service authorized by the FCC, and it has four main goals. First of all, to encourage the advancement in the art of science of radio. Second of all, to promote the development of emergency communication capability to assist communities when needed. Third, to develop a pool of trained radio operators. And fourth, to promote international goodwill by connecting private citizens in countries around the globe. Those are its charges for the amateur radio service. That's a lot of stuff. The good news here is that amateur radio is very flexible. There's fewer restrictions than other radio services. You have more frequencies that you can operate on. You can use more power. Just to give you some sense of that, if you're a licensed operator in the United States, you can operate a radio at 1,500 watts effective radiated power. In comparison, your walkie-talkie is about half a watt. Okay, so big difference there. More ways to communicate, and it's generally free, other than the hardware you have to pay for. And there's a large community of folks who do this. Okay, thousands across the United States, and many more than that around the world. How do you become an amateur radio operator? Well, you have to get a license. And there's, to get a license, there's actually different levels of licenses. The first one, entry level, is called the technician license, followed by the general, which is sort of an intermediate level, and then the amateur X, which is the advanced level. To get a license, you need to pass a test, okay? So typically for the technician exam, it's about 35 questions, multiple choice, drawn from a published pool over a variety of topics. And the good news is that if you're interested in this kind of thing, there's actually quite a bit of overlap between what we'll be doing in this course and what's actually on the technician exam. Let me just show you an example of that here. So on the left-hand side, you see sort of some common topics in this course. So things like charges, forces, and fields, electric potential, current resistance, DC resistor circuits, magnetic fields, electromagnetic induction. On the right-hand side, you see the technician curriculum. So you can see there's clear overlap here. Electricity components and circuits, definitely overlaps within circuits. Safety, amateur radio equipment, some overlap there as well. So, and if we get time at the end, we'll talk about more about fields and waves. That definitely overlaps with other things about radio signals and propagation, antennas, feed lines, that kind of thing. So, so if you're interested, I have here, I have some of these books which are, will allow you to kind of give you everything you need to know, basically, to get a license. It's got some chapters to talk about the various different topics, and at the end it has a list of all the questions that are going to be on the exam. So these are free to borrow for the term. If you're interested, please come talk to me. I'm happy to just have you sign a little form. You can take one with you today. Great for honors projects, if you do honors project. So I had several students, I had 3 students last term get licensed with that. Okay, so just want to mention that. It's kind of a nice thing to do. All right, getting into chapter 1 materials here, units, okay? There's going to be some new units which we'll talk about specifically for quantities having to do with electricity and magnetism. We'll get to those units, so specific units, when we get to that topic. But I did at least want to bring up these, remind you of the metric prefixes, because there may be a few that you haven't seen before, pending. So I'm sure there's some of you already know. For example, most people know about milli, 10 to the negative third, centi, 10 to the negative second, kilo, 10 to the third, things like millimeters, centimeters, kilometers. We will see in this course, though, some smaller units as well. So things like micro, 10 to the negative sixth as a multiplier, nano, 10 to the negative ninth as a multiplier, and even down to pico, 10 to the negative 12th. So people will talk about things like nanocoulombs for charge or picofarads for capacitance. Those are not uncommon. On the other side, we will also see some multipliers on the larger side. Mega, 10 to the sixth, giga, 10 to the ninth, and tera, 10 to the 12th. Okay? And so we'll see some examples of those today. I think a lot of times people hear about that in terms of computers, like megabytes, right? Gigabytes, terabytes. Okay, so just as a reminder, if you haven't seen these before, or if these are new, make sure you know these. Probably the one that's the trickiest one is these smaller ones. I remember the N and 9 because they start with the same letter. Right? That's how I remember that one. Okay, but again, we'll come back to units a little bit more, but just wanted to bring it up for now. All right, let's go back to the radio example. How many people listen to FM radio before? Okay, great. Almost everybody. So if somebody comes up to you, a friend, and says, look, I just heard about this great new radio station, right? You should listen to it. What do you need to know? What is it?
What frequency it is.
The frequency it is, right? What frequency it is. Okay? So frequency is a technical term, right? And we want to talk about what that is. That has to do with something has to do with electromagnetic waves, right? That's what radio waves are. So let's talk a little bit more about that. So radio waves are an example of a wave which occurs on the so-called electromagnetic spectrum. This is kind of all the different sort of ways electromagnetic energy can propagate from one place to another. As the name would suggest, a wave indicates something is changing, right? In this case, as we will see, it has to do with the changing of an electric field and a magnetic field. We haven't talked about what that is yet, but we will soon. So whenever you have something changing in a periodic fashion, that's usually called an oscillation. Every time you have one oscillation where the wave starts at a certain location and comes back to that same location or that same state, that's called a cycle. Okay. So then frequency, what does that mean in a technical definition? Frequency is the number of cycles that occur in a second, typically in the SI system. Okay? And as a result, that has a special unit associated with it. It's called the Hertz, H-E-R-T-Z, car rental company. Named, though, for Heinrich Hertz, who was an earlier investigator of electromagnetic waves. HZ is the singular. Now, whenever I have something that's changing, okay, so maybe I have a cycle that looks like this, right, changing in time, I could also ask, well, how long does it take for that cycle to start at a certain point, and get back to that certain point. That time that it takes is called the period, okay? So if your frequency is in hertz, then your period in SI units would be in seconds, okay? Another term that you'll often see then is the term harmonic, okay? A harmonic is a signal which has an integral multiple of a base frequency, sometimes called the fundamental frequency, okay? So if my fundamental frequency is 100 hertz, 100 oscillations per second, then my harmonics would be what? Fundamental frequency is 100 hertz. Yeah.
200, 300, and so on.
200, 300, 400, and so on. Right? Those would be your harmonics. So this occurs in electromagnetic waves, also occurs in things like audio systems. You may hear harmonics. That's another place you'll hear about it as well. Okay, so here's some pictures that will help to sort of maybe make some of these things a little clearer. So again, here's my, suppose I have something which is oscillating here. I have some terms I want to use to describe that sort of, that wave. The first one is called the amplitude. The amplitude tells me how big is the change, okay? That's on the vertical axis here. This is amplitude as a function of time. If this is an electromagnetic wave, that has to do with the strength of the electric field. If it's a sound wave, it may be pressure, some pressure level. So also frequency, okay, in this case here, that's the number of oscillations per unit time, right? So for example, if this were, say, 2 seconds, 1 second, let's make it 1 second, then I would have a frequency of 2 cycles per second. Right? Two cycles to get to that 1 second duration. It would be 2 hertz. The period is the time it takes to go from one point in the cycle to the same point as it repeats. So you can look at that maybe from peak to peak, or from zero crossing to zero crossing, zero crossing. And so that's considered one time, 1 cycle. Okay? That's the period. Again, sort of graphically, we can see the relationship between fundamental frequency here. In this case, the fundamental frequency is 3 cycles per second. So I can see then second harmonic would be 6 cycles, third harmonic, 9 cycles, integer multiples. Last term that you should know is a wavelength. So as I'm talking to you, right, yes, the sound pressure is changing, okay, but it's also traveling, right? It's traveling from me to you. And in that case then, not only do we have changes in time, we have changes in space as well, right? So if we were to plot, say, an amplitude of a wave as a function of position, now we can ask how far does it take for that wave to repeat, okay? And that's then called the wavelength. So you can see that here, often given by the symbol lambda. And here from zero crossing to zero crossing, whatever that distance happens to be, that's the wavelength. Okay? So these are some basic terminology of waves that you'll come across if you start studying waves in general. Any questions about any of these things? Okay, well, just some basics. Now, there's a sort of interesting thing here is that there's actually a relationship between the wavelength of a wave, this particular electromagnetic wave, and its frequency, right? So, first of all, let me ask a question. How fast does an electromagnetic wave travel? Anybody know?
The speed of light.
Did somebody say something?
Doesn't travel like the speed of light?
Speed of light, okay. Does anybody know what the speed of light is?
No.
Fast. Large number.
Fast,
300
okay.
million meters a second or something like that?
What is it?
300 million something meters a second?
300 million meters per second, roughly. Okay. Technically, 299,458 or 792,458 meters per second is the actual value, defined by standards. But yeah, oftentimes you'll see it as written as the letter C as 3 times 10 to the 8th, 300 million meters per second. Yes, it is. Okay, so if I know then that and this is something that Einstein taught us, right? The electromagnetic waves always travel at the speed of light. It's the fastest thing that can go. If I know that's the case, Then if I time out, it takes for the time for this wave to start at a certain point and then repeat back to that same point. If I know that time, okay, let's call it capital T, then how far does the wave travel during that time? I'm driving in a car, going 50 miles an hour. I drive for 2 hours. How far do I go? 100 miles. How did you get that? Multiply the velocity times the time, right? Distance equals rate times time, right? And that's no different here. So if we think about distance equals rate times time, in this case, my distance is going to be my wavelength, okay? My rate is going to be my speed of light, and my time is going to be my period. Right? Time it takes for the cycle to repeat. Okay, now that's great. Now, but we know also that the period is related to the frequency. How is the period related to the frequency? Well, if I have more oscillations per second, right, my period is going to be smaller. Yeah? So as I increase my frequency, my period should decrease. Because the wave to oscillate quicker and quicker and quicker, right, to make that happen. So the period then we see is going to be inversely proportional to the frequency. As your frequency goes up, period goes down. Right? Does that make sense? Okay. So if we put these two things together then, right, what do we find? Well, what we find is then that if you stick this in here, then we find that the wavelength is equal to the speed of light divided by the frequency. Okay? That's essentially the equation down at the bottom of the page. Okay? So, yes, wavelength and frequency are related to one another. Now, in particular, if we go ahead and we put in the value here, we can write lambda is equal to 300 times 10 to the 6th, and that's in, sorry, maybe write it this way. So it's essentially 300 megameters per second, right? And we divide that by frequency. If we put that frequency in megahertz, right? Remember, megahertz is 1 over time. So what we find is the megas cancel, time cancels, and we get then our wavelength in meters. Okay? So kind of a shorthand way to remember this for these electromagnetic waves, if you take 300, divide by the frequency in units of megahertz, that will give you the wavelength in meters. All right? So that's another formula to remember. Any questions here? Okay, so nice relationship between frequency and wavelength. All right, next up, I want to give you a little sort of walking tour through at least the radio part of the spectrum, and then we'll talk about other things after that. So you can start as low as 0 hertz, not so interesting, but oftentimes people, once they start talking about radio spectrum, they start down what's called the VLF part of the spectrum. So VLF stands for very low frequency, okay? Very low frequency electromagnetic waves are between 3,000 hertz, 3,000 oscillations per second, 3 kilohertz, and 30 kilohertz. 3,000 to 30,000. LF, you guessed it, low frequency, okay? Now that's between, so this is 3,000 to 30,000, and this is 30,000 to 300,000, okay? Oscillations per second. There are some natural phenomena which are in the VLF and LF range, but a lot of the practical things starts when we get up to a little bit higher. So MF, what do you think the M stands for?
Medium frequency.
Medium, yeah, you're right. Not very creative naming here. Medium frequency, and that's actually the home of the AM broadcast band. Anybody know what the range of frequencies are for AM radio? Yeah.
Like 100 to like 900 or something like that.
In the ballpark, not quite exactly. Anybody want to add on that? I know people don't really listen to AM radio much anymore. But it's going to be roughly about, I think it's about 540 to about 1,300. I think it's maybe even 500. Maybe it was 500. 500, about 1,300 kilohertz. Okay. So that's definitely in this range from 300 to 3,000. About 3 minutes, sorry. Okay. All right, so All right, so that's your medium frequency band. We get up to the HF band. What do you think H stands for?
High frequency.
High frequency, yep, you got it. So in that case then, high frequency band, this is the home of what's called shortwave radio. Anybody ever listen to shortwave radio? No. Sometimes if you get some more sophisticated radios, they'll have shortwave, you can select shortwave bands. This was much more common back before the internet, when countries were trying to broadcast information from one to the other. For example, the United States used to have a service, and they actually still have a service, called Voice of America. You try to put information about democracy into Eastern Europe and the Soviet Union. Shortwave band, okay? You still can listen to that band. All right, getting up a little bit higher, VHF, what do you think that stands for?
Very high frequency.
Very high frequency, okay? Very high frequency. And that is the home of, well, first of all, VHF television, over-the-air television, and also FM radio, right? What is the range frequencies for FM radio? Remember?
130.
Okay. Sure. Okay. Yeah.
Like 80 to 110?
What is it?
About 80 to 110?
80 to 110. Yeah, pretty close. I think it starts around 87, and I think it goes up to about 108 that would be megahertz. Okay, and your FM dial. Okay, that's usually the range of frequencies in the United States anyway for FM broadcast band radio. VHF is a little below that. But again, in this 30 megahertz to 300 megahertz range, that's your VHF band. Again, go up another order of magnitude, 300 to, in this case now, 3,000 megahertz or 3 gigahertz. That is the home of UHF television. So that's usually, so VHF television is channels 2 through about 19, and then UHF television is about channels 20 through, I think, 68 or 70. Also the home of mobile phones. Anybody know what frequency mobile phones typically operate at for cellular service?
100 something.
Typically, there were about 900 megahertz, okay? And you can see that's definitely in the mobile phone band there. Can be a little higher depending on what kind of service you have. All right, so again, and UHF stands for ultra high frequency. And this keeps going up, super high frequency, extra high frequency, et cetera, et cetera. Again, not very creative names.
Makes sense though.
Can you think of anything that's in the super high frequency band? You've all used it.
Deep.
Computer.
Was this something with the computer?
Computer.
Like what?
A laptop.
Okay.
Wi-Fi?
Wi-Fi, yeah. What frequencies is Wi-Fi operated, you know?
5 gigahertz?
Can be, that's on the high end, right? Typically about 2.4 or 5 gigahertz. That's usually the range or so, okay? So your Wi-Fi is going to be in here, okay? All right, so, yeah, lots of interesting stuff in this, even in this small amount of, actually pretty wide amount of radio wave bands. And I will note here, as we go up in frequency, our wavelength goes down, right? So let's take, for example, if I'm at 30 megahertz, what is my wavelength? No. 30 megahertz, what is my wavelength?
10 million meters?
A little shorter than that. Let's go back to our formula. Okay? We take 300, divide by our frequency in megahertz. So 30 megahertz. That's my wavelength. 10. Right? 300 divided by 30, 10 meters. As I go up, though, right? So, for example, if I go now to, say, 300 megahertz, so rid of that VHF band, what's my wavelength? 1. Okay. And that's why this is in multiples of 3. Right? So it's basically 10 meters, 10 meters, 1 meter, 0.1 meters, 0.01 meters, etc. Okay? That's your wavelength ranges. So there's quite a wide range, very, very long, hundreds of meters, down to just tens of centimeters. Okay. Any questions here? Yeah.
Does higher frequency mean like faster,
Faster in terms of what?
like crossing distance faster?
No, because the speed of light is always constant. Yeah, so it doesn't go faster. Now, you can have a higher rate of information communication or information transfer, because if you can make shorter pulses, you can send more information. So that's why that's why they're always trying to go to higher and higher frequencies. So, for example, you can send more data over 5 gigahertz Wi-Fi than you can over 2.4 gigahertz Wi-Fi. But the speed of travel is actually the same.
So why don't they all just use like ultra frequency?
Great question. So the engineering compromise here is that as you go to higher and higher frequency, your range goes down. Okay, higher frequencies are much more highly scattered and absorbed by buildings, walls, et cetera, et cetera. Right. So that's the downside. So, good question. All right. Interesting enough, though, this is only one very small section of the overall electromagnetic spectrum. So far, everything we've discussed is down here in this little green band, okay, from roughly here to here, okay? These are some of the things we've talked about, right? But you can keep going. So, for example, you go up to about 10 to the 12th terahertz range. Those are called terahertz waves. Those are sometimes now used in security screening, right? So sometimes you go to the airport, put your hands up like this. Sometimes those are terahertz wave machines. If you keep going up to about 10 to the 14th, 10 to 13, 10 to the 14th, that's infrared band, okay? Your infrared remote controls using that frequency band. This little section right here, around 10 to the little less than 10 to the 15th hertz, that's your visible light range, okay? So wavelengths from order about 400 to 700 nanometers. So again, as we go up in frequency, our wavelengths continues to go down and down, down, or below a millimeter. You can see that here. So this here shows you the wavelength as you continue on. So here we are, wavelengths in the order of the size of bacteria or viruses. Keep going up, 10 to 15, 10 to 16, that's ultraviolet. Okay, so that's the high end. And even beyond that, 10 to the 18, 10 to 19, 10 to 20th, X-rays and gamma rays. Okay? Now, there is a distinction between, when you get around the ultraviolet range, you'll see there's this little bar here, right? We go from what's called non-ionizing radiation to ionizing radiation. What does that mean? Well, as we go up in frequency, it turns out the photons, the bits of energy which carry the electromagnetic energy, go up as well. Right? So as we go to higher frequency, we get higher energy. And at some point, we get enough energy in the little photons that they can actually boot electrons out of atoms. Okay? So now I can ionize my atoms, right? Especially when you have living beings like us, right? That can be damaging. It starts to damage your DNA, damage your cells, and that's where you start to have issues. That's why you don't want to lay out for 4 hours on sunscreen on the beach, right? Because you get sunburn, maybe even skin cancer, okay, if you do nothing. Okay, so this is a very busy slide. I encourage you to take a look at it at home. I'll post these up, all the slides will be posted up. Yeah. Just take a look at it, it's pretty interesting. Any questions here, though? Okay. All right. All right, let's do a little quick check-in here. Make sure you're keeping up what's going on here. So here's the question. What is the relationship between wavelength and frequency? A, wavelength gets longer as frequency increases. B, wavelength gets shorter as frequency increases. C, wavelength and frequency are unrelated. Or D, wavelength and frequency increase as the path length between the receiver and the sender increases. What do you think the answer is here? Can we get your cards out here? Great. Let's do a poll here. Please vote now. Yes, so this one, B, is the correct answer. In fact, you were correct. It's shorter as frequency increases. We know that because we know that lambda equals C over F. So as F gets bigger, wavelength gets smaller. Okay, great. Super. All right. All right. So that brings us to the end of the preliminary chapter 1. So make sure you go read that. There's some additional details in that chapter. All right. Right. in the time we have left, then I'm going to get started on the next chapter, which is the electric field. Okay. Okay. All right, so let's talk about this. So chapter 2 then is dedicated to electric field. So the goal of this chapter is to describe electric phenomena in terms of charges, forces, and fields, particularly electric field. And see if we can explain what's happening to our unfortunate kitty here in this picture. Okay, so one of the things we want to first talk about is charge. So if I say the word charge to you, what comes to mind? Give me some examples here. Yep.
Static electricity.
Static electricity. Example of that? Sorry. Static electricity. Good. Okay. Anything else that comes to mind? Yep.
Electrons.
Electrodes. Okay.
Electrons.
Electrons. Sorry. Yeah. Electrons. Yep. Electrons involved with charge. Yep. What else?
Potential energy.
Potential energy could be involved. Yeah. Sure. We'll take that a little later in the course, but yeah. Right there. What else? Charge. What comes to mind with charge? Yeah.
Batteries.
Batteries, right? We've got to charge up your battery, right? So batteries have to do something with charge. I'm not sure yet what it is. What else? Charge comes to mind. One more? Okay. So these are good examples to get started with. What about, it's raining really hard outside. What do you expect to see oftentimes? Umbrellas, but electrical. Any electrical you expect to see? Yeah.
Lighting.
Light. Okay, lighting. That's usually has something to do with charge, right? Lighting is another good example. Okay. All right, so we got some good examples here. Charges around us all the time. So to kind of do our first little experiment here, what I'm going to do is I'm going to pass out to you styrofoam cups, okay? In these styrofoam cups, most of these will have either paper bits or foil bits. And if you don't have any paper bits or foil bits, actually this one doesn't missing some, so I'll wash first. So take one of these, you want to take these, we'll pass these out, and you'll have these paper bits and foil bits inside. What I want you to do then is, once you get the cup, see if you can start rubbing the cup against, well, first of all, dump out the paper and foil bits. And then you can start to rub the cup against various things and see if you can get any response in the experiments here, okay? Great, I had experimentation here. Let's get some observations here. What did you notice? What did you notice when you did your experiments here? Did you find? Yep.
That depending on where you rub on the cup, it's only that spot that actually holds the sag charge.
Oh, okay. So basically what you're saying is that it appears that the effect is only appears where you rub on the cup, is that right? Appears. Where you rub on the cup. Okay. So if you rub on one side, it doesn't really do much on the other side. Okay, great. Super. All right, other observations here. Yeah, you're fine.
Whenever you touch metal, it kind of grounds the cup.
Okay, so you can remove the effect from the, okay, by touching metal. Okay, so touching metal removes touching effect, okay. Okay. What else? Yeah.
The foil came up easier than the paper.
Foil came up easier than paper. Let's do a little poll on that. How many people found the foil was easier than the paper? Okay, great. How many people the paper is easier than the foil? Oh, okay. So I've got some divergence of opinion there, but mostly it seems as though most people had the foil was easier. It's easier to pick up. As compared to the paper. closely, okay? What else? Other observations? Did it matter what you rubbed on? Or what was better to rub on? What did you find? Yeah.
I was able to rub my watch and it picked up the grease.
Okay, what's your watch made of?
It's an Apple Watch, so
Plastic?
I guess.
Okay, I'm not sure. I don't have Apple Watch. All right, so we'll see. Okay, so better to rub. Let's see, better to rub. Let's see, we got an Apple Watch. What else?
Hair.
Hair. Okay. Hair seems to be working. What else do you find? 12. Sweatshirt. Okay. Sweatshirt. Okay. Anything else? Yeah.
Hair.
Hair. Okay, we got hair. Okay. Super. Anything that didn't work well?
The table?
Table didn't work well, okay. Not well. We got a table.
Notebook.
What else? Let me out. Anything else that didn't work well? No? Okay, any other observations you want to make? Okay, great. These are all good observations, okay. So we're gonna now go ahead and start constructing what we're gonna call a charge model. What do I mean by a charge model? A model is something, it's kind of a collection of observations that help try to explain something, right? And so, in this case, the first point I want to write down, I think hopefully you agree with this now that you've done some experiments, is that frictional forces like rubbing add what we're going to call charge to an object, okay? And the more rubbing creates more charge. Does everybody agree with that? Raise your hand if you agree with that. Okay, so most folks. Great, all right, so we had some other observations here, we'll come back to those shortly. Right, so that's what the first point of our charge model. Hopefully you've seen this in your experiments. All right, so next up, I want to show you a couple of videos. Again, I want you to take a look at the videos and then see what observations you make, and see what else we can build into our charge model. So let me explain what you're going to see here. This is basically a stand, and then on this stand there's a very thin string right here, which goes down to a what's called a pith ball. Pith ball originally was made out of a light woody plant called pith. Now typically they're made out of styrofoam, but it's just basically a light little ball. Okay, so I'm going to go ahead and play this video. Okay, there's no real audio here, but I'll turn the audio on anyway. But all right, so what you see here is first of all a coated plastic rod. Back there. So as we take that plastic rod and we're going to rub it against a piece of silk. Experiment here. This is what's called ebonite rubber. It's a rubber rod. Take that rubber rod and then rub it against the fur. Okay, so that's the first video. Second video. In this case, again, with pith balls. In this case, now 2 pith balls, also on thin strings. And I'm going to rub a plastic rod against the silk. This effect. Okay. Now I'm going to take the rubber rod, and rub it against the fur. That's the second video. All right, so 2 videos here. What did you observe in those videos? Give me some observations. What did you notice? Yeah.
Two
positive charges causing the balls to go opposite directions, like repelling each other.
So you're doing the second video?
Yeah.
Second video, okay, yeah. So we saw then that at least when the two pith balls were touched with the same object, same charged rod, they were repelled. Okay, yeah, that's a good observation. What else did you notice here? Yeah.
The fur and rubber seem to have hold a stronger charge or give off a stronger charge compared to the silica and plastic tube.
Okay, so maybe possibly the fur rubber combination seemed to be a stronger effect than the other case. Okay, so let's write that down. Rubber, perhaps stronger effect than the plastic and silk combination there. Okay, great. Other observations? Yep.
They only seem to repel after he rubbed the shafts.
Sorry, one more time?
Like before he rubbed them down with the fur itself, they had no effect on the balls.
Oh, okay, yeah, so we had sort of a control experiment, where we put in nothing, this uncharged object, and you rub it, and now then there was a traction or repulsion?
Proportion. Or no, attraction of the first video.
Traction, first video, right. So, once we had it, when you bring the charged object, charged rod, in both cases, next to pith ball, you get traction, okay? And notice that and that was even with pith ball had not been touched, right? What else? What about the second part of the second video? Right, so the two balls come apart, right? Then what happened? Brought in the rubber rod. What happened then?
The balls attracted?
Yeah, it was attracting. It was attracting. That's sort of interesting. So in the first case, in the first video, the pith balls were not touched, right? But in the second video, they were already touched. And they were still in attraction, right? After that. So so the rubber rod attracted the two pith balls charged by the plastic rod. Okay, that's sort of interesting as well. Okay, so yeah, these are all great observations. I'd like to make some sense of this. What's going on here? So I'm going to add a few things to our charge model. So hopefully then what you saw is that there's at least two different kinds of charge. Okay, so we have some sort of charge which results from rubbing the plastic and the silk. We have another kind of sort of charge that results from the rubber and the fur. I'm going to go further than that and assert that there's only two kinds of charge. Right? So we will, of course, sort of later associate this with positive and negative. Second of all, hopefully you saw from the videos that, and from your experiments even, that like charges exert repulsive forces. That's the two pith balls that were charged with the same charge, right? Those are like charges that repel. But unlike charges exert attractive forces, right? So the rubber rod, which is a different kind of charge, attracted those pith balls, which were charged by the plastic rod. So unlike attract, like repel. Number 4, the electric force is considered a long-range force. What do I mean by that? If I want to move this cart, okay, I have to physically touch the cart. Right? I don't have any Jedi mind tricks where I kind of used to just think about it and make the cart move, right? I gotta touch it. That's not a long-range force, that's just a contact force. But here, right, we saw the pith balls would move. You didn't have to get right on top of it and touch it. You could get just close to it, right? And that still had some effect. So the electric force is a long-range force, and hopefully, we didn't do this quantitatively, but maybe you saw it with your experiment. Did you notice that as you got closer and closer, you got a bigger effect? Yeah? Further and further away, not so much, right? So it matters how close you are, right? So the magnitude of the force decreases with distance between the objects and increases with the amount of charge, right? So as was observed, if I put more charge on my object, it was easier to pick up, say, the paper and foil beds. Did you see that? Okay. So this is another observation we want to make. And number 5 here, we're going to define a term called neutral. Right? So a neutral object is one in which has equal amounts of each kind of charge. Okay? So when we say something is a neutral object, we're not saying that it has no charge. Okay? We're saying that there's a balance between one kind of charge and the other kind of charge. So why do we say that? Well, because that sort of helps to explain why rubbing works to charge an object, right? If I can pull away some of one kind of charge from an object, I leave an imbalance in the first object, right? That's why rubbing seems to cause charging. Right? We take a neutral object, we separate the charge, now we get two charged objects as a result. Okay? All right. So, yeah, we have here. Let's do this one problem here. We have a minute left. Okay, so let's try this example. Then suppose we have now three pith balls, each suspended from thin threads. We're going to rub various objects against other objects, and each of the pith balls is touched with one of these objects. At the end of the experiment, we find the following. We find that pith ball 1 and pith ball 2 repel each other, and pith balls 2 and pith ball 3 also repel each other. From this, we can conclude that, here are your choices, A, 1 and 3 carry charges of opposite sign, opposite type of charge. B, 1 and 3 carry charges of the same type of charge, same equal sign. C, all 3 carry charges of the same sign, same type of charge. D, one object carries no charge. Or E, we need to do more experiments to determine the sign or type of charge. So think about that for a minute here. What's going on in this experiment? You ready to vote? Let's do a vote now. Please vote now. Okay. So I'm seeing A's and B's and C's. Okay, A's and B's and C's. All right. So anybody want to give me an argument for your answer? Why did you pick your answer? Yeah. What'd you pick?
I picked C.
Okay. Why did you pick C?
Well, 1 and 2 repel each other. It means that, and 2 and 3 repel each other. It means 1 and 3 also repel each other, causing all of them to be the same.
Okay. So that's an argument for C. We had some other votes for A's and B's. Anybody want to give me their arguments for A's and B's? A or B? Yeah. What do you got?
Both 1 and 3, both repel 2, or repel from 2, so I would say 1 and 3 have the same charge.
So you voted for B?
Yeah.
B. Okay, so I'm going for B. Okay. Any other arguments here? Okay. Right. So correct answer here is in fact C. Okay. All 3 charges carry charges of the same sign. Right. So here's the logic. So I know that 1 repels 2. Right. They must have the same sign. We know like charges repel. Right. 2 and 3 also repel. They must also be the same sign. Right. And so in that case, then 1 is the same as 2, and 2 is the same as 3. They all have to be the same. Okay. So here our answer is C. All 3 carry charges of the same sign. Okay. Questions?
So wait, if there is an object with a neutral charge and then one with a positive charge, what happens?
Good question. Let's go back to the first video, right? Pith ball was hanging from a string. It had not been touched with anything. It was neutral. What happened when you brought in the charged rod?
They attracted the.
Attracted. So neutral objects are attracted by charged objects. Okay. Good question. All right, we're pretty much here at time. We'll stop here. We'll come back and we'll continue on this on Thursday. So again, by Thursday, should have read chapter 2, should have taken the reading quiz for chapter 2, and hopefully also got started on the homework. Right, at least get your account set up for that. Okay, make sure it's working. Let's do homework's due on Thursday.